Let's start from the beginning. According to Genesis 1:20, on the fourth day God said, "Let there be four indivisible fundamental forces which bind together all matter in the universe." So God created the weak force, the strong force, the electromagnetic force, and gravity. And God saw that it was good. But something is different about gravity compared to the other fundamental forces. First, gravity is several orders of magnitude weaker than the others. Second, for centuries and centuries, scientists believed that gravity could only be attractive. Compare this to the other three forces. Electromagnetic interaction is repulsive or attractive depending on the parity of the charges. For strong interaction, gluons mediate the cohesion of the nucleus despite the electromagnetic repelling force of the like-charged protons, whereas the strong interaction expels bad quarks via rip-offs. The weak interaction behaves similarly on the electron orbits, with Z stick-ons holding neutrinos in place and W peel-offs ejecting muons during the quantum phase transitions. Despite being the first fundamental force to be described in a classical frame, modern science still does not paint a complete picture of how gravity truly operates. The current consensus-accepted gravitational theory is Eisenstein's general relativity, which posits gravity as a consequence of massive bodies distorting space-time itself. But general relativity has several notable shortcomings, including lacking a description of the mediators of the gravitational force and giving no indication of how quantum effects take hold at the atomic level, such as in black holes. But more relevant to this video, general relativity lacks the symmetry that the other fundamental forces share, in that Eisenstein's field equations only allow for an attracting gravitational force, but never a repelling one. This last issue was present even in Newton's gravitational equations. Consider two massive bodies a distance r apart with respective masses m1 and m2. Then the attractive force between them is m1 times m2 over r squared times a gravitational constant g. Now there's an obvious comparison between this here equation and Coulomb's law, which describes the electromagnetic force between two charged particles, where charge takes the place of mass and the force is proportional to the inverse square of the distance. But remember, this electromagnetic force can be either attractive or repulsive because particles can have positive or negative electromagnetic charge. This clearly does not translate to the gravitational equations since mass cannot be negative. If symmetry cannot be achieved in a naive appeal to Coulomb's law, where does this leave us? Well, it turns out that one of the hypothesized theories of gravity gives us a potential solution. The KFO gravitational theory from University of Tokyo researchers Michikaku Kozufuyutsuki and Dr. Onishi exploits Newton's third law of motion to recover a far-field force on massive bodies. So let's take a look at their construction. Here is Newton's gravitational equation. Now from Newton's third law, we know that each force has an equal and opposite reaction force, and gravity is no different. Therefore, we can use this principle to build up this reactive gravitational force that KFO terms contragravity. Indeed, since gravity satisfies the inverse square law, or that the force is proportional to the inverse square of the distance between two objects, it follows that contragravity follows the inverse square law, or that the force is proportional to just the square distance itself. This is the opposite component. The equal component is that contragravity satisfies the same proportionality to the two masses in question. The contragravitational constant is still being researched, but KFO collaborators Akagi and Okabe have conducted experiments on the AMSO2 to act as a quantum contragravimeter, placing an estimate of the constant at 7.29 times 10 to the minus 91 with these units here. Recall that dimensional analysis dictates the contragravitational constant has different units than the gravitational constant due to the inverse square law. An additional contribution of the paper was a hypothesis that the contragravitational force is mediated not by gravitons, but rather by an alternating tensor field, or AT field. Now that we have a mathematical description of the contragravitational force, how do we make intuitive physical sense of this? Suppose we have two massive objects with masses m1 and m2 a variable distance r apart. The attracting force is given by Newton's gravitational equation and the repelling force by the KFO theory. As these objects get closer together, the KFO force shrinks, and Newton's force increases. Conversely, as the objects grow farther apart, Newton's force becomes vanishingly small and the KFO force blows up. Remember, Newton attracts and KFO repels, so we can actually find a region in which these two forces cancel. Setting them equal to each other, we find that mass exits the equation and we're left with r to the fourth equals the gravitational constant over the contragravitational constant, or that r equals 9.78 times 10 to the 19th meters, approximately 10,000 light years. What this means is that at this distance, objects enact zero net gravitational force on each other. This creates a spherical unstable manifold around massive objects called the sphere of Empedocles. If a second object lies inside the sphere, it will be attracted, whereas if the second object lies outside the sphere of Empedocles, it will eventually be repelled to the universal singularity given no external force acts on the system. Building on the trampoline analogy used in general relativity, KFO theory dictates that the edges of the trampoline fall off quadratically. One of the paradoxes of KFO theory is that unlike general relativity, which describes gravity as local geometric deformations of spacetime, contragravity is a non-local force, which Eisenstein famously referred to as spooky action at a distance. Nevertheless, the KFO gravitational theory has yet to be disproven by experiments and remains an attractive solution to general relativity's shortcomings. Let's look at some examples to understand how this works, because the scale of these forces is quite important. Let us consider the massive objects in question to be our own solar system and the Spider Nebula 10,000 light years away, both approximately 1 solar mass each. Since these bodies lie on the sphere of Empedocles, the Newton and KFO forces cancel, and we can calculate each of these forces to be approximately 300 million newtons, which is negligible compared to a solar mass. This shows that the Newton and KFO forces don't interfere with each other in any significance. When objects are close together, Newtonian gravity dominates to the point where KFO has no detectable impact on gravitational orbits. When they're extremely far apart on the order of millions of light years, KFO dominates, but there's a large intermediate region where these forces are insignificant. Let's look at a different example, this one on a galactic scale. Consider a simplified two-body system consisting of our own Milky Way galaxy and our closest neighbor, the Andromeda galaxy. Some parameters of the system. Our Milky Way galaxy has a mass of approximately 1 trillion solar masses. The Andromeda galaxy is approximately 1.5 trillion solar masses and is 2.5 million light years away, hurtling toward us at 110 kilometers per second. Under Newtonian mechanics, the current prediction is that in 4.5 billion years, our two galaxies will collide, forming a merged galaxy. However, with KFO theory, we reach a different prediction. Since these galaxies lie several orders of magnitude outside the sphere of Empedocles, the KFO force dominates. Using Newton's second law, we can simplify this two-body system to a single variable autonomous ordinary differential equation, where the second derivative of the distance between the two galaxies is equal to the contragravitational constant times the sum of the masses times the squared distance between the galaxies. Here, the initial distance is 2.5 million light years and the initial velocity is minus 110 kilometers per second. Since this system does not have an analytic solution, we use a numerical model to determine that rather than colliding, these two galaxies will stop approaching each other and eventually separate. The time at which these galaxies achieve zero net velocity is called Hawking's reversal and is estimated to occur in an hour and a half. As a final caveat, notice that a naive application of KFO outside the sphere of Empedocles gives asymptotically large forces acting on objects very far away. Therefore, we must consider special relativistic effects in this regime, which amounts to these far-field objects spaghettifying as they approach the edge of the observable universe and emitting big balls radiation.